Hello class, it's Mr. Ofsted with lesson 3 of unit 6. We're going to take a look at the energetic side of simple harmonic motion. So lesson 1, we were able to see how the kinematics and dynamics of simple harmonic motion worked. Now we're going to look at the dynamics. The energetics. We already looked at dynamics. So with energetics, right, we're always thinking about work and energy and joules. So let's take a look at something that's fairly familiar by now, this horizontal spring system undergoing simple harmonic motion. We know that when it's at its maximum compression, we have no velocity, it's at rest, so we have zero kinetic energy, right? But we also know that this spring right now, being under this compression, is fully loaded. It has this maximum X value, and the spring potential energy therefore is a max, because that spring energy is equal to half of our K value times our X value squared. For those of us who do not remember the energy formula for a spring, also given on our formula sheet under energetics. So when we have maximum displacement from equilibrium, we have maximum spring energy, but that also comes at zero kinetic energy. In the middle here, we have zero displacement from equilibrium. We're at equilibrium, so we have zero spring potential energy or elastic stored energy, however you want to look at it. But we're moving at the fastest speed, right? V is a maximum value at equilibrium. So we're going to kind of switch between maximum spring energy to maximum kinetic energy and back again, as we're constantly going through this back and forth simple harmonic motion. So we got to remember conservation of energy here, right? That's our principle of physics 5. So we're never going to be creating or destroying energy. It's just transforming from stored potential in the spring to kinetic in the movement of that mass. So it's always going to be equal spring and equal kinetic at their max values. And if you looked at some point midway between, it would have part stored potential, part kinetic, equaling up to that total energy in the system. So like I showed here, we've got half of kx squared as our spring energy when k is, or x is max. That's our maximum stored potential energy. And half of mv squared is our kinetic, even more familiar formula. And when speed is max, our kinetic energy is max. All right, so now we're just throwing in our simple harmonic motion vocabulary, with amplitude being the maximum displacement of our distance from equilibrium. So that's the amplitude of this simple harmonic motion. So A for amplitude, and we're still keeping our speed the same. So we can rearrange this formula to solve for our max speed when we know our amplitude and our spring constant and our mass. This one isn't given on our formula sheet, unfortunately, but we should be able to work with this conservation of energy quite simply. Right? Just like in our 4th unit, energetics, we weren't given a conservation of energy formula on our formula sheet, but we are given all of the pieces that combine to it. So they're not, this isn't directly there, but both the pieces for it, right, half of kx squared, half of mv squared, are given under the energetics portion of our formula sheet, if we're looking for that. And interestingly, this is the same for vertical simple harmonic motion, because the the gravity will cancel itself out. So I'm not going to prove that. If you want to have a little bit of fun, you can try to do your energy analysis in the vertical as well. We're going to be throwing in gravitational potential energy as well as spring potential energy and kinetic energy. So there's going to be 3 different energy transfers going on in this one. It's a pretty fun one for you to explore on your own. But just remember that this will work for both horizontal and vertical springs. All right, another short set of notes. Let's give our example a go here. Doesn't matter if it's vertical or horizontal. This one is vertical, so we'll see how that works itself out here. A mass is attached to a spring with a stiffness of 6.1 meters. So we'll start by drawing it out. As always, we have our spring and a mass on it. We don't know what that mass is, but we do know the spring stiffness is 6.10 newtons per meter. Right, and it's going to be bobbing up and down. That's not really how it's going to look, but you get the idea. We have this vertical simple harmonic motion. The mass is bobbing up and down with 14 cycles in 19.5 seconds. So 14 cycles in 19.5 seconds. We know the max speed is 7.7 meters per second. We want to find the amplitude, right, which is our distance from equilibrium at its max point. All right, let's first make some sense out of this. We want to find period, our formula for Vmax is amplitude times the square root spring constant over mass. And we also have, from previous lesson, period is equal to 2 pi square root of m over k. So those are going to be the formulas we're going to end up using. We're given this information about cycles and time. We're going to use that to find period first. So find our period of oscillation or of bouncing, however you want to think about it. The period, capital T, is always equal to the number of cycles divided by, time over number of cycles. I was doing frequency. Period is always in seconds, so we need time. So the time total divided by the number of cycles. So the total time they give us is 19.5 seconds, and we're doing 14 cycles in that time. So our period comes out as 1.393 seconds for 1 cycle. Right, so that's going to be our period, 1.393 seconds. All right, we're given this speed. We are given this spring constant K, but we are not given mass. So in order to solve for our unknown, this is what we're worried about, the amplitude, we first need to find mass. The question doesn't give us anything about mass. So we need to kind of think about this in terms of the forces acting on it, right? We have force of gravity, we have force of the spring. And we remember from lesson 2 with our period, we have this formula, which includes mass. So if we know the spring constant and we know the period, we can solve for mass. So that's what we're going to do next. We're going to find the mass. That's a bit of a jump, and it's going to take some practice on your part, that when you aren't given mass, but you are given a spring constant and a way to find period or a period, right? We can determine mass using this period of simple harmonic motion equation that's on our formula sheet that we went over in lesson 2. So finding mass, we're going to need to do some algebra. We're starting with period is 2 pi square root of m over k. And again, we're going to have to square everything. So when we square everything, we're getting rid of the square root on that one side. We're getting d squared is 4 pi squared. Don't forget about the 4 pi squared times mass over spring constant. So last lesson we solved for k from this. Now we're going to solve for mass. So mass is already on top. Instead, we're going to multiply both sides by k and divide by 4 pi squared. So we have mass by itself is equal to 4 pi squared cancels. We get spring constant times period squared, those two guys on top on our numerator, and 4 pi squared on our denominator. So again, the algebra of this can be a little bit tricky, but that's what we're left with. And we can throw in our values. Our spring constant was 6.1 newtons per meter. Remember, we need our standard units when we're throwing them in an equation. This one was given as a standard. Period needs to be in seconds for it to be standard, which we solved it for 1.393 seconds. And that needs to be squared. That's going to be a common mistake. Don't forget to square your period. And we're going to divide it by 4 pi squared. That's going to be another. These pesky squares are going to be your biggest enemy with this lesson. So throw that in our calculator. 6.1, 1.393 squared divided by 4 pi squared. We get a mass of 0.2998 kilograms. Kilograms is coming from our newtons, which is mass times acceleration, right? Seconds squared will cancel out the seconds of acceleration, and meters will cancel out the meters of acceleration. We're left with kilograms. So that's the mass that is suspended, 0.29, pretty much 0.3 kilograms. But we're going to keep our significant digits all the way to the end. Now we have mass, we have our spring constant, we have our speed max, we're looking for amplitude. We're ready for our last part of this 3-part question. Find amplitude. So from this new equation that we derive this lesson from our kinetic energy equal to our spring energy, max speed is equal to the amplitude times the square root k over m. So this one, algebraically, a little bit easier. We don't need to square everything. If we're solving for amplitude, you can actually put in the values first, right? I'll show you what I mean. We don't have to do a bunch of squares and algebra. We know that our Vmax was 7.7 meters per second. That's going to be equal to our unknown amplitude times the square root of k, which was 6.1, divided by mass, which we calculated as 0.2998. So we have 7.7 is equal to 4.511 times our amplitude. We're just going to divide both sides by this. And we're left with our amplitude, which is equal to 7.7 divided by 4.511, or 1.71 meters. And that's our final answer. You could algebraically solve for it by squaring everything and then taking a square root, or by multiplying by the reciprocal. Right, so if we multiply this by the square root of m over k and did the same thing over here, right, the amplitude is going to be equal to 7.7 or Vmax times the square root of 0.298 divided by 6.1, the reciprocal of this guy. That is all for lesson 3, the energy. This homework will really test your problem solving skills. Try your best with it. It's going to take some outside of the box thinking. Don't give up right away. But if you are getting stuck and feel like you're just banging your head against the wall and not making any progress, feel free to send me an email and we will work on it together. All right, good work everybody. Thanks for watching. I will talk to you later.